Okay, now I want to spend a little time talking about going from what I call old nuclear to new nuclear. There's a lot of acronyms here. This is the graphite thorium reactor. In the popular social media, it's called liquid fluoride thorium reactor. And in Oak Ridge, it was called the two-fluid molten salt breeder reactor. They're all the same thing, okay? Only differences in small details. So there are lots of people in the audience that are more expert about nuclear fission than me, but there are probably also some people who are less expert than me. So I'll just give a very quick review of nuclear energy in a nutshell. For fission, all right, not fusion. So fission, you need fuel that's capable of fissioning, and that word for that is fissile. And there are only three in practice. They all are odd number for a technical reason. You have to have an odd number of neutrons and even number of protons. So the ones that we use today is uranium-235, odd. Okay, that's only 0.7% of uranium. One that we hope, some people hope we can use is plutonium-239, and what I'll talk about from thorium is uranium-233. These are not naturally existing, but you can get them. You can get something that's what's called fertile, make it into something that's fissile by adding excess neutrons. When you add a neutron to something that's fissile, this has too many neutrons, so it breaks. It vibrates and breaks into two. Those have even more neutrons than they'd like, so they typically spit out 2 or 3 neutrons, these fission products. All right? So the fact that it's greater than 1 means you can sustain a chain reaction. The fact that it's greater than 2 means you can use that extra one to make something fissile, which was only fertile, and maybe make even more if you're very economical of the neutrons. So that's how you do it. You add a neutron to uranium-238, which is the other abundant isotope. It's 99.3% of natural uranium. Becomes uranium-239. 2 of the neutrons decay into protons, and you get plutonium-239, which is relatively long-lived. And that's most of the community, when they talk about breeder reactors, that's the cycle they talk about. But there's another cycle that China and India are very interested in, because neither country has uranium, but has thorium. Thorium has only one isotope, thorium-232. So if you add a neutron to thorium-232, you get 2 thorium-233, 2 beta decays, and you get uranium-233, which is fissile. That's 100% of thorium. So the way we use nuclear reactor today is that natural uranium is very hard to use by itself because there's so little fissile. So typically, in a light water reactor, you would do isotope separation to enrich the amount of uranium-235 from 0.7% to a higher value, typically about 5%. But if you count both the stuff, you have 2 piles, some that you took over here, so this becomes depleted, this becomes enriched. If you count both, the fuel efficiency is still only 0.7%, and you get a little of plutonium, so it turns out it's about 0.3%, and then the rest is depleted uranium and plutonium-239, which some of which you get to burn. Now, what do you do with this waste? All right? Well, one way you can do it, take depleted uranium, you put them on tanks, military tanks. Okay, they can stop shell. But how many tanks does the world need? So that's not a big market. Okay, so basically, the rest is what people call nuclear waste, 99%. So the way we use uranium today, we use 1%, throw away the 99%. And we're awful at throwing away the 99%. No one even knows how to do that very well. So that's the model we have. However, this is not to denigrate present reactors. It's a very good design. It uses ordinary water as the coolant of the core. So you generate heat. You want to transfer this heat to something more easy to handle and that you can do something. So the easiest thing is to, say, turn it into steam. So, so that's the heat transfer ordinary water. The hydrogen in water is well matched to the mass of neutrons, so it's very efficient at slowing down neutrons, which makes the reactions easier. Okay, cross sections larger. Okay, both of what's called a moderator, and it absorbs neutrons. And those two characteristics make actually nuclear reactors very safe in terms of never running away. The thing you're afraid of is loss of coolant accidents. Okay, that's what happened at Fukushima. That's what happened at 3 Mile Island. That's what happened in Chernobyl. It's not stopping the reaction, because as long as you lose the coolant, you've lost the moderator. So it stops itself. All this, nonsense that people spread, the fear that nuclear reactors are bomb, that's nonsense. No reactor has run away. All right? They all stop themselves. But you have the fission products, and they continue to release heat, and they may cause meltdowns. Okay? And that's the danger. It's from that decay heat, okay? Which was not done well in the 3 examples I talked about. Now, there are 2 kinds of reactor built by Canada and by the former Soviet Union, which uses not light water, but heavy water in the case of CANDU reactors, where deuterium substitute for hydrogen. You see, deuterium is a hydrogen that ate a neutron back in the Big Bang. And so it doesn't want any more neutrons. So it's a very good moderator without absorbing neutrons. And graphite, that's the other thing that can slow down neutrons without absorbing it. And that's what was used at the Russian design. But they also use water as a coolant. That was a disastrous combination. Graphite moderated, water cooled, disastrous. Now when you lose the water, you don't lose any moderator, but you lost the absorber. So what was critical now is supercritical. Okay? So that's very bad design. Everybody knew it. Okay? So when people bring out Chernobyl as an example, that's not going to ever happen again, even in Russia. Everybody has learned their lesson. Now, breeder reactors, there's basically 2 that are in contention. One was pushed forward by Argonne National Lab. Other groups have taken up. Now it's split off and become the Idaho National Lab, where you don't moderate. You use fast neutrons. It turns out if you don't moderate, you need much more fuel to get critical, but it's also much easier to breed plutonium. All right? To get the coolant so it doesn't absorb many neutrons, you can use liquid sodium as a coolant. Now, if you know any chemistry, you know liquid sodium is a tricky substance. It touches air, it's on fire. It touches water, you have an explosion. Okay? So it's not impossible. People are still attempting to go this route, but it's not easy. All right? The other route is the Oak Ridge National Lab, about 50 years ago, where you slow down the neutrons using graphite, but now you don't use water. You use molten salt also to cool it, and that is breathing. Okay, now thorium-232 is a byproduct of rare earth mining. Its abundance is about 4 times uranium-238. So that turns something which is basically unsustainable. If we were to use light water reactors and only use 1% of the uranium, this may be only 10 years before the high quality uranium is gone. If you can breed into plutonium, it's up by a factor of 100, so 1,000 years. If you use thorium, it's 4,000 years. 4,000 years is almost the age of human civilization. We better have fusion by then, otherwise we should kick all the plasma physicists out of university. Okay, so let me give you a schematic way. So here's another theme that I will use over and over again. Don't use the word waste. Nature doesn't know the word waste. It always reuses waste. If you want to be sustainable, the equivalent is no waste. Every waste should be turned into a resource. That's the only way to make things economical. Waste, people think, oh, 我要花钱, I have to spend money to. But if it becomes a resource, you can earn money. Then people would do it. If you have to spend money, everybody's reluctant to do it. Okay? So try to turn waste into a resource. And that's what this graphite thorium reactor or lifter or two-fluid molten salt breeder reactor. So you start with nuclear waste from light water reactors. So you have uranium-238, uranium-235 that didn't get transformed or didn't burn. So you take that out or separate it chemically, and you give it to people who want to build fast reactor, the integral fast reactor, or Bill Gates who wants to build the traveling wave reactor. They can use it. The leftover plutonium and higher actinides, you can use the process of pyroprocessing and use that as a fuel. That is a fuel, all right? It has excess neutrons, so if you surround that with thorium in a form of a salt, the excess neutrons will come out of the core and turn the thorium into uranium-233. Very dilute, so how do you get it out? Well, this is a liquid, so if you take some portion of it and you add fluorine gas or hydrogen fluoride, there's a process called fluoride volatility where uranium F6, not uranium F4, turns from a liquid into a gas. A gas and a liquid will just bubble up, will just separate by itself. You turn it back into a liquid, you put it into the core, and now you have what's a breeder reactor. So you use the waste, it's like a match, like a pilot light, you get it started, but once you get it started, it becomes self-sustaining, okay? So that's a breeder reactor, this is a converter reactor. Now, the difficult things with fission products, of course, you have to also get out. You have to do it by chemistry. And this was the argument between Fermi, who pushed the sodium reactor, and Wigner, two Nobel Prize winning physicists. Wigner was a Nobel Prize winning physicist, but his undergraduate degree was chemical engineering. So he knew, unlike all these physicists who think they're so smart, okay, but very rarely know any chemistry, okay? He knew if you want to do chemistry, the best phase to do it in is a liquid, not a solid. Solid, you have to melt it into a liquid, and you have to refabricate. He knew if you have a liquid, you can do continuous processing so that removing the fission products becomes relatively easy. Not easy, but relatively easy. So that was the great insight of Oak Ridge, which was run by a protege at that time of Wigner's, which was Eugene Wigner. So this is the graphitic core module that we got SGL polycarbon to build for us. S stands for Siemens, G stands for graphite, and L is a company in Southern California that they took over. Everybody takes over companies and make what's on sale. Okay, you want to buy it, you can get. So they built this for us. This is nuclear grade graphite where we cross drill holes so that the channels don't cross. So here we send fuel salt. When it meets the bottom, it turns up, it goes back up. So it just circulates as a pump, as a cycle. So we don't let it do anything other than transfer heat to the blanket salt, which carries the thorium. As it's carried into this reaction zone, it's irradiated with neutrons, so you also turned it into new fuel, which then you use chemistry to put into the fuel salt channels. So you need nuts and bolts, and you need things that conceal these things. And this is carbon composites, okay? I won't go into the details. A group from Caltech, based in Caltech, has made some YouTube videos of this thing, and you can go on to YouTube, Raw Science, and click on this thing. Anyway, here's the basic points. Because you're talking about fluids, it's possible to safely extract uranium-233, and you always make some uranium-232, which is proliferation resistant for reasons I won't talk about, in this pool. This is surrounded by a large pool, which carries a blanket salt, bifluoride volatility. Now, how do you get out all of the fission products? Fission products, 很讨厌啊. It's everywhere. Left-hand side of the periodic table, right-hand side of the periodic, middle of the periodic table. If you have to extract each one by one, it's 很讨厌. Okay? So it's a very simple way to get rid of them. Leave them behind. Extract the solvent. Okay? Vacuum distill the solvent after you've taken out. Then you just leave behind. That's the ultimate waste. Okay? Even that's not a waste. Those of you who do nuclear medicine, nuclear batteries, know we shouldn't be calling that stuff waste. It's useful. If you have a light that you don't trust to go out, okay, or a pump that you need to turn on, don't use a chemical battery like Fukushima. You should use nuclear batteries. Okay? Exit sign. That's powered by tritium. Did you know that? Okay? Lighthouses in the Arctic cannot go out. That's powered by strontium-90. So these are resources that we should make use of once we get over this irrational fear of low-level radiation. Okay, so it's safe. There's another aspect which convinced me as an astrophysicist. You see, when I went to Tsinghua Daxue, I had to understand what people like him did. And they're very vocal. They insist I understand what they did. So I had to read up on different kinds of reactors so I could talk, sensibly to them. And what I discovered, what this reactor does, why it can regulate itself, I said, oh, this is ultimate in safety. Why? Because it's self-regulating. It's what the experts call load following. Why is it load following? Well, remember I said you extract the heat by pumping on the blanket cell. If I pump harder, I'm cooling it down, right? When it cools, it contracts like any liquid, goes into the core and speeds up the rate of nuclear reaction. So when you want power, it gives you more power. If you want less power, you pump less hot. It gets hotter. It expands out. Reactions go slow. That's exactly how the sun works. Okay, I'm an astrophysicist. You have to take my word. Exactly how the sun works. There's no operator running the sun, yet you can depend on the sun tomorrow being like it was today, if you can see it. Okay? It is safe, just like the sun is safe. Okay? So, how much footprint does it have? Well, nuclear power, this is something that people don't realize, is so much more than nuclear energy. It's millions of times more powerful than any form of chemical energy, which is 1,000,000 times more powerful than most forms of mechanical energy. Right? That's why fossil fuels beats wind. You put in a few liters of gasoline, 车子可以动, right? 跑得很快, right? Think about powering it with wind turbine. Very difficult. Nuclear energy is 1,000,000 times more than that. So what is a footprint? It's the tip of your little finger. Okay, that's your environmental footprint per person. It's not zero waste, but it's practically zero waste. Okay, so let me just finish. I've already getting close. How you can turn seawater into fuel. By now, you won't be surprised. It's a salt cycle. Okay? So, how do you turn water into oxygen and hydrogen? Well, every high school student has been probably shown this experiment. You can do it with electrolysis. You hook up a battery to electrodes, cap it with a test tube, and on one side you get oxygen, on the other side out comes hydrogen. So why don't we do this? The reason is because the electricity that you used in the battery is worth more economically than the hydrogen and the oxygen does it. So nobody would do this. Not economically feasible. The other way you can do it is to add heat. No batteries, just add heat. Well, simple calculation. What does it take to dissociate water? 3,000 Celsius. Okay? Well, most you now ask Professor Liu, can you give me an alloy? He'll say, I can do it, but it's very expensive. Okay? So you won't do it either. But, so nobody does it. But this is the holy grail. Now, it turns out that using a copper chloride cycle, there are 3 steps you can actually do it economically. The first is you don't dissociate water, you dissociate hydrochloric acid, or HCl, with copper chloride. Copper is a transition metal, so it can either have 1 chloride or can have 2 chlorides. And so using a little electricity, the copper chloride can help you extract that chlorine, leaving behind the hydrogen. So that's how you get the hydrogen. So how do you get the hydrogen chloride, the hydrochloric acid? Well, you take this copper chloride too, and you react it with water. All right, you get them back with this salt, the hydrogen chloride plus copper oxygen chloride. So this helps extract the oxygen away from water. Finally, this can be heated up to get a molten chloride, which is what you had to start with, to give you oxygen. All right? And the temperature you need here is only 530 degrees. Now, the amount of energy that you need to expend here is maybe only 1/10 compared to direct electrolysis. The 90% of it is supplied by heat. But heat is cheap, not like electricity, which is expensive. Especially nuclear heat or burning charcoal or coal is cheap. So this becomes economical, all right? At reasonable temperatures that Professor Liu can say, oh, I have a hope of giving you an alloy like that, but you might have to wait till next week. Okay? So the full cycle turns water plus heat plus electricity to give you hydrogen and oxygen. Now, Atomic Energy of Canada Limited can do the first two steps. And we've been talking to them. Molten salt is something we think we can do easily. And they've also done an estimate, cost estimate, where if they use solar energy for the heat, they think they can produce 1 kilogram of hydrogen for 17 Hong Kong dollars. Okay? Now, 1 kilogram of hydrogen is equivalent, roughly, to 1 gallon of gasoline equivalent. So I hope you're still partly on the imperial unit, so all of you know what 1 gallon or even 1 US gallon is. How much does that cost in Hong Kong dollars? Much more than 17 Hong Kong dollars, right? So certainly in Hong Kong, it would be worth it to do it. And if you can get even cheaper heat, it will be even worth it in the United States or Europe or almost anywhere in the world. So that's a way that you can do it. Now, let me belabor the point. One has to realize fossil fuels are deeply embedded in every aspect of industrialization. It's not only energy. It's how we make fertilizer. It's how we make electricity, etc. Okay? For example, if you get oxygen, you can do carbon sequestration very easily. You burn something that has carbon in it, you get only carbon dioxide. Right? Why can't we do that and bury the carbon dioxide to sequester carbon? It's because if you burn it in air, there's a lot of nitrogen, much more than oxygen. And so you're spending all your time, money, burying nitrogen. Nobody would do that. Okay? So they want to do it, so then you have to separate the carbon dioxide from the nitrogen. That's not an easy process. Adds to the cost. That's why very few people are willing to do it. But if you burn it with oxygen, then it's easy. It's all carbon dioxide. You bury it, it becomes carbon negative. If your carbon source is carbon neutral, and now you bury its product, it becomes carbon negative. Hydrogen fuel cells, all right, I won't talk about it. When people talk about hydrogen fuel cells, that's a solution. Is it a solution? Where do you get the hydrogen? Right now, we get it from fossil fuels, from methane, from methanol, from whatever. Okay? But if you get it from seawater, it really becomes fertilizer. All right? How do you capture nitrogen? Plants, very few plants can capture nitrogen in a usable form. So the way that it's been done ever since Haber and Bosch won the Nobel Prize for discovering it is to combine it with hydrogen to get ammonia. You combine ammonia with carbon dioxide, you get urea and water. Okay? And that's a carbon neutral fertilizer. Fertilizer, you may realize, is responsible for 75% of the so-called green revolution. If we didn't have fertilizer from the chemical industry, we would only be able to support 1/4 of the world population that we have today. So we don't have a choice easily in the near term except to continue making fertilizer, but in a much more friendly way. All right? So this is, I'm not saying we should all do this. I'm sure somebody will do this if you give them the basic tools. So that's where now, here's another slide. I'm always having to refer to Kaizizong. When I talked to him the first about building a graphite thorium reactor, his reaction was, do you know how much nuclear-grade graphite? Do you remember this? He says, this is the equivalent of gold. You know, it's so expensive a material. It's equivalent to gold. Well, I've done a little research, and you're almost right. It's as expensive as silver. Okay. But it's worth it. So here, how do we get the cooperation of the oil companies? If we want them to stop burning oil, why would they do that? We say, you know, these are stranded assets. They're not going to do it. They're going to use all their power, all their money to influence the politicians, as they are. You must say, you can earn even more money by not burning the oil. What is that? Well, we already know what that process is. It is this. The fossil fuel industry can move up the value chain. So today we make nylon from oil. If you take nylon fiber, which is you can make in any arbitrary length, you heat it up to 900 degrees, it becomes carbon. It becomes very weak. But if you heat it up to 2,800 and higher, it graphitizes. It becomes very strong bonds, which becomes a fiber. Okay? That fiber you can make of arbitrary length. Stronger than steel, lighter than steel. If you have fiber, you twist it, you get yarn. If you weave the yarn, you get fabric. And once you have fabric, you can make anything. Okay? That is carbon fiber technology. Okay? So here's a carbon fiber fabric. What can you make out of it? You can make airplanes. Okay? You can make nuclear reactors. How much is this worth? So this is very funny units. A Boeing 787 is worth about $1,000 per kilogram. Okay? That's less than gold. More like silver. Okay? Kaizizong was right in direction. Molten salt breeder reactor, we have to add one more step because this set's full of holes. Okay? You have to seal up the holes. It'll be more than $1,000 per kilogram. Without sealing it, it's also $1,000 per kilogram because it's that choice. We know. We bought one of these. That's what it costs, $1,000 per kilogram. So there's only a few industries that can afford this at today's prices. High-end luxury cars, airplanes, nuclear reactors. But eventually, this material should supplant other kinds of building materials or add to the repertoire of building things. Lighter than steel, stronger than steel.